So, hello students, and welcome to Hedu Math Hub. In this video, we'll be taking a quick, one short overview or quick revision of this very important topic, sound waves. Jamb cannot skip this topic. They always bring questions from this topic every year. So we're going to be focusing on this topic, sound waves. So let's start like this. Please, if you're online, make sure you react, okay? Like this channel, subscribe. You can post your comments in your questions in the comment section. I'm taking them one by one. Okay, you're welcome to the live. This is Edu Math Hub. Thank you for supporting this channel. I really appreciate all your efforts. And I believe that you guys will win in this Jamb 2025. I believe you're going to be successful. So let's start this class like this now. So the first thing we're going to be talking about is the definition of sound waves. So let's go like this. So before we define sound waves, we're going to talk about waves in general. Waves. So I'm going to give you a basic idea of waves. So what's a wave? So a wave can be defined as a disturbance. That's the first thing you need to know. A wave is a disturbance. Okay? And it's a disturbance which travels outward from a source. That's to tell you that a wave has a source. That's a starting point where it begins from. Okay? That's the starting point. So a wave is a disturbance which travels outward from a source, carrying energy along with it. That's the basic definition of a wave. A wave is a disturbance which carries energy, okay, and it travels outward from a source. That's to tell you that a wave can be used to do work. Wave has the ability to do work because waves have energy. So these guys, they possess energy. I know energy is the ability to do work. That's the first thing you need to know. The disturbance travels out from the source, okay, and carries energy. Now, bearing that in mind, you can see this example here. When you throw a stone, this is a water body here. You now throw a stone into it. You know, the stone will form ripples, like circular ripples like this. Those ripples will originate or start from where the stone landed in the water. And the ripples will flow out like this. As in, they'll be flowing out like this. In like circular curved manner, starting from a particular point. That point is where the stone actually landed. Okay, this is where the stone landed. So this disturbance, the water might be still at first. The water will be still, as in it's not moving at all. But when you now throw the stone into it, that means you have disturbed that particular medium. You now see the sound waves moving outward like this. So that's to tell you that a wave has been generated at that point. Okay, now let's move on. Now, this is an example of what is called a water wave. A water wave. Okay, this is the wave generated in water. Now, so at times it might also look like this if the particles are in this sinusoidal like sine form. So you can see that at this point the particles are at a higher displacement, or you can say they are at a higher crest or amplitude. They have moved higher. At this point, they are at a lower amplitude. Okay, so the direction of propagation of this wave, the wave is traveling like this, is moving from left to right. But as it's moving from left to right, it is also going up and down. As in, it is going up, down, up, down, up, down. You can see my marker is moving. My marker is going from left to right like this. As I'm going from left to right, I'm also going up, down, up, down. So the motion of these particles of this wave is going up, down, but the wave is traveling in this direction. So that will give you an idea of how the particles move in relevance to the direction of propagation of the wave. So that will bring us to types of waves. So we have types of waves now. So types of waves. So we'll take the first one. The first one, we're going to talk about transverse waves. So if you look at transverse waves, you understand what I just drew at that beginning, but when I was talking about water waves, you get a basic idea of it. So what's a transverse wave? A transverse wave is a wave in which the particle displacement are perpendicular to the direction of propagation of the wave. The particles are moving up and down, but the wave is moving from left to right. So the particle displacement, as in the up and down motion of the particles, okay, the up and down motion of these particles, like this, up, down, is at right angles to the direction of the movement of the wave. So you can see the particles are going up, down, Okay, they're going up, down, up, down, up, down, but the wave is going from left to right. So you can see they are at right angles. This kind of wave is called a transverse wave. Okay, so a wave in which the particle displacement are perpendicular to the direction along which the wave travels is called a transverse wave. A popular example of this kind of wave is water waves. So you have water waves. It's a popular example of a transverse wave. So keep that in mind. So you can also include light waves and other waves like that. So, but let's keep this one in mind that a popular example of transverse wave is water waves. So let's move on to the next one. We're going to look at the next one, which is electromagnetic waves. So let's talk about mechanical waves first. Okay. So you have mechanical waves. So if something is mechanical, that means it requires a medium. So this kind of waves, these are waves that require a medium function. They need a medium. They require a medium. So mechanical waves are waves that require a material medium for their propagation. As in, you cannot create this kind of wave without having a material medium. So a popular example of this kind of wave is sound wave. You cannot produce sound wave without having a material medium. Okay, so keep that in mind. A popular example is sound wave. Move to the next one, which is electromagnetic waves. This one is very, very important. Jamb can also ask you, so take note of that. There are questions that come out every year based on this particular part. So we're going to talk about electromagnetic waves now. So electromagnetic waves. So these waves, they do not require any material medium. So they need no material medium. No material medium is needed. No material medium, okay, is needed for the propagation. So if you want to generate this kind of wave, you don't need any medium. Okay, a popular example of this kind of wave is light wave. Okay, light wave does not need any material medium. It can travel in vacuum. It can travel in water. Light wave can pass through water. It can also pass through vacuum. So light wave is an electromagnetic wave. So you can also have radio waves too. Radio waves is also an example of electromagnetic wave. Okay, so they are also transverse in nature. Okay, they are transverse in the sense that the particles move up and down like this, and the wave moves in this direction. So light wave, sorry, light wave, one, it is transverse. After that, light wave is also electromagnetic. That's the short form. So it does not require medium, and it travels at right angles to the direction of propagation of the wave. Then we'll move to the next one, which are longitudinal waves. So longitudinal waves are also very important. So these are waves in which the particle displacement are parallel to the direction of propagation of the wave. So the way the particles are moving, okay, it is parallel to the direction of propagation of the wave, like this. So the particles might be moving like this, in parallel with the direction in which the wave is traveling. A popular example of this kind of wave is sound wave. Sound wave is a longitudinal wave, and sound wave needs a material medium. Sound wave cannot travel in vacuum. It's not possible. It needs a material medium. So sound wave is a mechanical wave. It is not electromagnetic. It is a mechanical wave. It is mechanical in nature, and it needs a material medium. It is also longitudinal because the direction of propagation of the wave is parallel, or is in the same direction as the displacement or movement of the particles of the medium. Okay, so I hope you understand these few parts. Now let's look at another one, which is the graphical. This is the next part. Graphical representation of a wave. How is a wave represented? Now this part is important. So follow up. Don't be left behind. Don't be left behind. So I hope you're preparing for your jump. Jump is coming. So prepare for it. I believe you blast it. Don't worry. Just follow up, okay? Follow up. Now a wave can be represented with this small chart here. This graphical this depiction of a wave. So this is the displacement. You can use X to represent this displacement. Like, let me just say Y. Then let me just represent this part with displacement, which is X. So it goes like this. You can also call this place time, depends on the variable you are using. So this is the depiction of a wave. So from here, so these 0 points like this. This is the graphical depiction of a wave. So this point here is the region of maximum displacement. So you call it amplitude. Okay, maximum displacement. Then this point here is the region of minimum displacement. So it's also amplitude, but it is in the negative direction. This is minus A. You trace it well. This one is positive A. Okay, so take note of that. At this point here, where the height of the wave is high, you call this place a crest. This is a crest. And the point where it is low like this, you call it trough. So this is a trough, and this is a crest. So a crest is the highest point of the wave. You can see this is the highest point of the wave. This is the highest point of the wave. A crest will always occur at the amplitude. Okay, it occurs at the amplitude. Okay, after that, you know what is called the trough. The trough is the lowest point of the wave. This is a point of very high pressure where the particles are closer together. Okay, so the lowest point of the wave is called a trough, as you can see here. This is crest, this is trough. Lowest point is crest, lowest point is trough, highest point is crest. So keep that in mind. This is the region of maximum displacement. Then you need to know what is also called the amplitude. I've talked about that. That's just this distance. Distance from here to here is the amplitude, which is A. Then you need to also know what is called the wavelength of the wave. Now this wavelength, the symbol is lambda, and the unit is meter. So wavelength is measured in meters. So the wavelength is the distance from crest to crest, the distance from one crest to another, or the distance between any two successive crests, or any distance between two successive troughs. So if you have something like this, and this is the nature of the wave going like this, the distance from this highest height here to this highest height here is wavelength. So you can use it like this. You can just write lambda. That is the distance between them. Let me just say W, but the symbol is not W. Let me just use W. This is the wavelength from here to here. The distance between two successive crests or trough. Then this is another trough. This is a trough. This is T, the lowest point. Lowest point. The distance between the two of them is also called wavelength. Or you can use this symbol here, lambda. Now this thing is very, very important because Jamb will always ask you. You need to be able to know this point. And you also need to know the point that are in phase. When you say something is in phase, that means they move together. They move at the same point. Okay, if you have a point going like this, this is point. Let me say this point here is point A. Then you have another point that is moving alongside with it. They are on the same straight line. They are moving alongside each other. Then that means they are in phase. That means they are becoming high at the same time, and they are becoming low at the same time. So from this graph, it is very important for you to know how to find if two points are in phase or if they are out of phase. So let me show you. It's very, very simple. Don't worry, it's very simple. So I'm going to use red color to signify that. Now look at these 2 points here. Let me put a mark here. I'm going to put a mark here now. This point here, let me call it A. Or let me just call it Y. And this point here, X. Let me say Z. These 2 points here, they are in phase. Why are they in phase? Because they became 0 at the same time. At this point here, the value is 0. This one too, the value is also 0. So point Y and point Z, they are in phase. Okay, now let me do another example so you understand it better. Let me just start it all over so you get it in a better view. Let me draw it again. Please listen up, listen very well. You get it now, don't worry. You get it now. Let me start from this point here. This is point Y. You can see that this is point Z. At this point here, this wave was going like this. It has reached its maximum point at point Y. At this point Z, it has also reached its maximum point. That means Y and Z, you can say Y is equals to Z because they are in phase. Hope you understand. They are in phase. So Y is equals to Z. Y is equals to Z. But if you look at another point, let me say here is A, for example. This point is A. This point is A. And let me say this place is B. So they might ask you, is point A and B in phase? Are they in phase? The answer is no, because point A is not equal to point B. The particles there are behaving differently. How will you know? Look at point A. This wave was going up like this, Abi. At this point, it's coming down. The particles at point A here, they're actually coming down. They are going down to zero. But the particles at point B here, they are going up. Because the wave is going up like this to point Z. So A and B are not in phase. They are not related. The particles are behaving differently. I hope you understand that. So you need to check the nature of the curve. If is it going up or going down? Let me check another one. Look at this point now. This point here. Let me put this point here as T. And let me pick another point here as maybe S. They can ask you, is S and T in phase? So let's check what's happening at T. So this is T here. You can see that at point T, this wave is coming down. It is falling down like this. It is going down. So that means the particles here are going down. Now go to point S and look at it too. Point S here, the particles are also going down too. So that means S and T are in phase. You can say T equals to S or S equals to T. So they're in phase because the particles there are behaving the same way. So I hope you understand that. Now, since we have done wavelength, the next thing to do is to look at frequency. So frequency can be defined as the number of complete vibrations per second. So frequency is the number of oscillations that the wave will make in a second. It's just like the symbol is F, first of all, and the unit of frequency is hertz. So the unit of frequency is hertz. So the first thing that this about frequency is just the number of like the vibrations that you have, like this like this, the number that you have. If it is much, if it's going like much like this, then that means the frequency is high. But if it's going like this, like it's far, they're far from each other, that means the frequency is low. So this kind of wave now, look at this wave for example. This wave, you can see the number of high and low it has a high frequency than this kind of wave. You understand? The number of vibrations that wave will make, that up and down, up and down, up and down motion that it will make in 1 second, okay, is what is called the frequency. Okay, now the reciprocal of frequency is what's called period. So period is the time it takes to complete one oscillation. That's period. The symbol for period is T and the unit is seconds. So the unit of period is seconds. So if look at this shape for example, the period is the time it will take this wave to move from here, come like this and go up again. So from this point here and this point here, these 2 points are in phase. Any 2 points that are in phase, that's like a period. So this is a period here. This is a period. From here to here is a period because it's as if the wave is starting again. You can see this distance. It's as if it's starting again from here, like this. It's as if it's starting again. So that's a period. So period is the time required for one complete oscillation. So keep that in mind. And frequency and period are related. F is equals to 1 over T. The reciprocal of period is frequency. And also T is equals to 1 over F. So if you keep these two things in mind, you cannot have any problem. And also a sine wave, this kind of sine wave can be represented mathematically using something like this. So this is a sine wave. This is the amplitude here. So you represent it like y. This is y here. This is x. So you see it like this in your text. So you have y is equals to a sine 2 pi over lambda vt minus x. is the mathematical equation of this wave. So I'll just give you the basic explanations. A is the amplitude. Okay, A is the amplitude. 2 pi over lambda vt minus x. So t is the time, where and A is the amplitude. I would also tell you things like phase angle later, and I'm going to tell you how to get omega, the formula between omega and frequency, and so we're going to do that one later. But for now, just know that this is the general form of the equation of a graphical sine wave. Now, I've given you the relationship. Now, there's a general wave equation formula, general wave equation formula. So the formula is V is equals to F lambda. Very, very important. In most sound wave calculation, electromagnetic calculation, this is the formula they use. So V is velocity, F is frequency, and this is wavelength. This one is called lambda. So V equals F lambda. Don't forget this. This one is measured in meter per second. F is measured in hertz. That's Hz. Why? You know the unit of wavelength already. Wavelength is measured in meters. So you just put these three guys together and you get the answer to any question. So move to the next one, which are properties of waves. Properties of waves. So properties of waves, we have the first one here. Waves can undergo some properties. Waves can undergo reflection. They can also undergo refraction. Waves can undergo diffraction. Jamb will ask you, so make sure you're taking your notes down. And please, if you're online, subscribe and react to this video. Okay, these are the properties of a wave. These are the basic properties of a wave. So reflection, refraction, diffraction, and interference. So let me just give you a quick overview of all of them so you understand them better. Jamb normally asks questions like this, probably in question 15 to 20. If you check your pack very well, you see questions on sound waves, even towards the ending part. So we have the first one, which is reflection. So reflection is very simple. Reflection is just what happens when a wave hits a medium. When the wave hits a barrier, you have a wave traveling like this, and the wave hits the barrier. It hits the barrier. No, the wave will travel back. It will travel back like this. That is reflection, basically. So when a wave is reflected upon itself after it encounters a barrier, then that is reflection. Okay, so at times this barrier where the wave is meeting might be a straight line, might be a plane like this. So let's assume the wave is entering like this. If the barrier is a plane, is smooth, then the angle of incidence like this, the angle with which the wave enter will be equal to the angle with which the wave will go out like this. Okay, so the angle of incidence will be equal to the angle of reflection. So this angle here is called, let me say y, let me say I, let me say r. So if it's very smooth like this case, angle of incidence will be equal to angle of reflection. That's when surface is smooth or surface is a plane. Okay, and another thing you need to take note of is that the angle of incidence is equal to the angle of reflection if it's a plane surface like this, and the speed and wavelength of the wave remain unchanged as long as they remain in the same medium after reflection. So when this wave hits a barrier, it will be reflected back into the medium. This part might be water, this part might be glass. So once the wave hits the medium, it will be reflected back. Let me say this place is water and this place is glass. So once the wave has hit the medium, it will bounce back. It was coming from water, so it will go back to water. So the speed will not change because it is being reflected back into the water. So some things will remain constant. During reflection, speed is constant. Speed is equals to k, it does not change. Wavelength is also equals to k, it does not change. As far as the wave is reflected back into the medium from which it came, these two can only change when the wave enters into the second medium. Maybe the part of the wave enters into the glass from air to glass, then there will be a change in the speed and the wavelength. So take note, speed and wavelength remain constant during reflection. Okay, as long as the wave remains in the medium in which it was coming from. The next one is refraction. So I'm going to explain refraction for you now. Refraction is very important. Follow up, follow up. Let's go, let's go, let's go. Let's cover this thing. Please follow up. If you don't understand anything, drop it in the comment section. Now, refraction is what occurs when a wave undergoes a change in wavelength. So during refraction, some things will change. So things that change during refraction, wavelength will change, speed will change, okay, but something will be constant. Frequency does not change. Frequency is equals to frequency doesn't change. So take note of that. During refraction, wavelength will change, speed will change, but frequency will not change. Let me tell you why. The reason is during refraction, the wave is entering to another medium. If this is glass and this is air, the wave is leaving glass. It is leaving glass and it is entering into air. So if this is the wave, for example, this is the wave here. This is the wave like this. This is the wave like this. It will refract. It will bend its direction when it gets to air. The reason why it changes direction is because of the density of where it is entering. Are the particles in that place, are they tight or are they close together, or are they far apart? That will determine how wide it's going to bend or how wide it's going to deflect. So you can see that it has changed direction. So the direction will change. That's the first thing. Another thing that will change is also direction. You can add that too. The direction will change, the wavelength will change, and the speed will change. The speed will change because the wave is entering into a denser medium or an optically less dense medium. If the medium is very dense, like glass, for example, glass is a solid, so the particles are very, very tight. So when the wave enter, the particles will try to block it from moving, so the wave will slow down. But if the wave is entering something like air has particles that are far apart, so as the wave is entering, it will move very fast because nothing is blocking it. So it will move fast depending on the medium in which it is entering. So we're going to talk about refraction and refractive index later. Now let's move on to the next part, which is diffraction. Now follow up, let's go. Now diffraction is very important because I've seen several questions like this coming out in your Jamb. So diffraction is what occurs when a wave encounters an obstacle, okay, whose dimension is about the same as the wavelength of the wave. So a wave is going like this, it now meets an obstacle that is blocking it. The wave will try to bend itself and pass along the obstacle to try to divert it. This is why if you're in your room, for example, this is your room here, and this is your parlor here, and somebody is calling your name from your parlor. The reason why you can hear that sound because you have like different wall settings in your house. As the person is calling your name here, the voice of that, the sound from that person, the sound wave will pass to this wall. It will dodge this wall, dodge here, dodge here, dodge here, dodge here until it gets to your own room and you hear the sound. So the sound the sound wave is diffracting. It is trying to dodge the obstacles until it gets to you. So diffraction it occurs when an obstacle, okay, when a wave encounters an obstacle, okay. So the wave will now bend. You try to bend around the obstacle. You try to dodge the obstacle. You try to dodge it and just pass through it like that. So it will move to the other part. So sound waves are diffracted around corners of a building, while radio waves are diffracted around hills. Radio waves can travel through long distance. So if you have a small building like this on the corners of a building, sound waves are always diffracted at that point. Okay, sound waves are diffracting. They are dodging the corners of a building, especially outside. Okay, they try to bend around the corners. So move to the next one, which is interference. So interference is very important. They might ask you what happens when two waves interact or when two waves meet. So this is what happens when two waves interact with each other. So interference is the superposition. Okay, the superposition of two waves. You have a wave going like this. You now put another wave again on top of it. So these two waves are superimposed. So at the point there will be the strength of one wave high. Sorry, the strength of the two waves will be high. At the point, the strength of the two waves will be low. So the strength of the two waves will be high at the point where two of them are moving at the same height. Like if this first wave now, second wave is now like this. You can see that this one is becoming high here. This one is also becoming high here. they are becoming high at the same point. So the strength of this wave will be high at this point. At the point where they became zero at the same time, it will be low. At this point where they have the same height, like one is reaching maximum, the other one to reaching maximum, they will also have a greater strength. So there are two types of interference. So the first one is constructive interference. So constructive interference is what occurs when the two waves they react positively. Okay, so they not cancel each other out. So one is going like this. The other one too is following that same pattern. It's following that same pattern. It's going the way it is going. They not cancel each other out. And this one is becoming high. That one too is becoming high. Like that. They're becoming high at the same point. So that is constructive interference. So this occurs when the two waves match each other, crest for crest and trough for trough. So this is trough here. This is one wave going like this. This is one wave going like this. This is the crest. This is wave A. This is the crest of the second one. You can see. Second wave is like this. This is the crest. This is the crest. This is the trough crest. You can see trough trough. They match straight line. Crest crest. They match straight line. So this is constructive interference. So the wave will be strengthened at that point. So when they are in phase with each other, in this case, the amplitude of the resulting wave is larger than the component wave. This point, so then their strength will, the amplitude will be very, very high because if you combine the amplitude of this one plus this one, so the answer you're going to get will be more than the amplitude of each of them. Take for example, use the amplitude of wave A. Imagine this is wave B. If wave B has the amplitude of maybe 10, and this one average of 20, when they combine, it will be 30. So that 30 is higher than the amplitude of each of them. So that's what happens in interference. So you also have what is called destructive interference. Destructive is when they cancel each other out. The strength of the waves, they cancel each other. This is destructive interference. So when the two wave trains or the waves are out of phase, when out of phase, something like this, this is the wave here. This one here is starting at the maximum point, going like this. But at the point where this one is starting, so it's coming down like this. This is the first wave. Let me say wave A. Now this other wave here is starting, is going like this. It's going like this. Sorry, let me just redraw it again. So if you compare them, you see that at this point 0, this is wave B. So at this point 0, wave A, this is wave A here. Wave A is already maximum, but wave B is starting from 0. It's as if you are doing relay. You are standing here. You not tell someone to stand in front of you. The other person is already ahead of you. You want to do race. You not give the person gap, 10 meters gap. The person is already in front of you. That means that person is leading you. You are at the back. You are lagging. You are at the back. So this wave B here is lagging wave A. Wave B is lagging at the back. So wave A is already leading. To confirm it, you will know from here. At this point, wave B is maximum already. But wave A is 0. You can see. They are not at the same maximum. Yeah, or they're also different. Unlike this one, where they are high at the same time, low at the same time. You understand? That is destructive interference. So this occurs when the two wave trains are out of phase, with the crest of one coinciding with the trough of the other one. Okay, the result is a reduced or zero amplitude. So the amplitude that will happen, or that will be resulting from this, will be a small amplitude. So you see it from here. This one will be small. This one will also be small. Two of them will cancel out because the height of one is meeting the minimum part of the second one. So they will cancel out. The final answer will be a reduced amplitude. So this one is polarization. So polarization is when it occurs only in take note of this. Jamb asked this question last year. They asked which of the following can be polarized. Polarization only occurs in transverse wave. Only transverse waves can be polarized. Take note. Polarization occurs only in transverse waves. It does not occur in longitudinal waves. There's waves that travel like this. That's what occurs in. So polarization is when you try to make a wave to travel in a single direction. So in a transverse wave, such as light, the vibration can be in any direction. Light, if you shine a torchlight, it will shine in different direction, it will shine in different direction. The light to brighten. But if you want the light to shine in a particular direction like this, you have to polarize it. This is what you have in laser. You know laser beam now? Laser beam that will shine at a particular point. If you turn on a laser beam at night, it's not everywhere that will become bright. Only a particular point will be lit or bright. That point where the red dot is, that's what you have in laser. So laser is polarized light. So polarization, it is possible under certain circumstances to restrict the vibration to one direction. So this is the vibration normally. This is a normal light wave here. This is the vibration. The vibration is in all directions. It's like this, it's also like this. It's in all directions. But if you want to polarize it, you will make that light wave to travel only one direction. So you will block other directions. So this is the light is coming in. So by the time it comes out, it will come out in a single direction like this. So it will allow only one. Let me say this vibration I want, only vertical vibration like this. That's what I want. I don't want these other ones that are like this, maybe like this, or like this, or like you block other ones. So this is what is called a polarizer to block it. So all this vibration will enter, vertical vibration. That's what I want. Then that is what will come out here, and the light will be focused on a particular spot. This is what will now give what is called a laser beam. So laser beam is a polarized light. The light has been constricted or restricted to flow in only one direction, blocking other vibrations in other directions. So it is possible under certain conditions to restrict the vibration to one direction only. So while vibrations in the other directions are cut off. So this phenomenon is known as polarization. So it only occurs in transverse wave. Please take note. They can ask in OBJ. Polarization only occurs in transverse wave. Sound wave cannot be polarized. Why? Because sound wave is a longitudinal wave. Sound wave is longitudinal. Light wave can be polarized. Why? Because light wave is transverse. So bear this in mind, okay? Now we'll move to what is called stationary waves. So stationary wave. Now stationary wave is also very important. Stationary wave is a wave that looks like this. You also call it standing wave. Standing wave. So this stationary wave here, you have something like this. Then you have a line that goes like this. So the waves are going like this, like this, like this, like this. So at this point here, you have what's called antinode, which is the region of maximum displacement. Then you also have this small point here. This is node. This point is node. It's called node N. This is antinode A. This is node N. This point where it meets with the x-axis is node. These are the nodes. So a stationary wave is what occurs when you have two waves that meet at a point and there's a reflection. So you have something like a wall like this. So when this original wave, this one at the top here, this one here, when it gets to this wall, it will be reflected back. It will not form this one that is under. So you have two waves moving at the same time. So you have what is called node and antinode acting at this point. So maximum displacement at the node, the region of minimum displacement at the node, maximum displacement at the antinode, minimum displacement at node. So now the points that are halfway in between two nodes, this is a node and this is a node. The points that are halfway in between two nodes, like this, you have something like this. This is node, this is node. The point that is halfway in between them is called antinode. This is A, this is also A. So this point is called an antinode, this point here. So antinode is located in between two nodes. Okay, and the distance from node to node is lambda over 2. So they can ask you what is the distance between two nodes. So from, let me just use DNN. Distance from node to node is lambda over 2, which is half a wavelength. So half a wavelength is the distance from node to node, and the distance from antinode to antinode is also lambda over 2. But the distance from node to antinode is lambda over 4. So you just divide this by 2. So you divide this part by 2. This half of it, because from here to here is lambda over 2. So you divide it by 2, you're going to get lambda over 4. Okay, I hope you understand. So now this is the part that is very, very interesting. So I want you to follow up very well. Now, if you have any question, please drop it in the comment section, and please try to like this video, subscribe, click the like button. I really appreciate you guys. You guys are wonderful. Now, don't forget what I just said now. Nodes are maximum displacement. Sorry, antinodes are maximum displacement. Nodes are minimum displacement. Okay, you can see it from these charts here. Now let's move to the next one, which is the production of sound waves. So, production of sound waves. How are sound waves produced? Now, production of sound waves is very special because we use sound every day, right? So how does sound produced? Sound waves are produced when there's a vibration, okay, of a body. When the air particles around something vibrates. When it vibrates, then it produces a sound. Sound waves are majorly produced by vibrating bodies. If something does not vibrate, it cannot produce sound. Sound waves are produced by vibrating bodies. Okay, vibrating bodies. That is what produces sound. Okay, so this vibrating body will moving to and fro. As it moves to and fro, it causes the air particles near it to vibrate, and that would causes two regions. So the first region is called regions of compressions, where they have the air particles closer together, and you have regions of refractions, where you have the air particles that are when they are farther apart. So compressed air, regions of compressed air are called compressions, where you have the density, the pressure is very high at this point, and you have refractions where you have low pressure or where the particles are far apart. So this alternation as in from compression to refraction produces the sound. So the sound which travels away from its source. I told you guys from the beginning that a wave travels away from its source. The point where a wave started, the wave will be traveling away from that point. The wave does not travel to its source. It travels away from where it started from. Okay, so it travels at a particular speed too, which is given by v, and the formula can also be v equals to f lambda. Just check the frequency multiplied by the wavelength, so you get the velocity. Okay, so sound waves also require a material medium. I told you sound waves are mechanical waves. They are mechanical in nature. So sound waves cannot travel in a vacuum. Take note, Jamb asked this question last year. Sound waves cannot pass through a vacuum. Okay, very important. Sound waves cannot pass through vacuum, but though they require a material medium. Sound waves can pass through wire. They can also pass through water and other materials, but they cannot pass through where there's no air at all because they need a material medium. They need air particles to make them move. Okay, that is why they are different from light waves, because light waves are electromagnetic in nature. Light waves do not need a material medium to propagate. So move to the next one. Sound waves, you also need to know about the speed which sound waves travel. Sound waves, the speed of sound is about 330. It depends on temperature, meter per second at 0 degrees C. That's the speed of sound. Speed of sound is 330 meter per second at 0 degrees C. So it depends on temperature. Speed of sound depends on temperature. Okay, and sound waves travel very fast in materials like water, concrete, then glass. The speed of sound in these three materials is higher than the speed of sound in air. This is the speed of sound in air, 330 meter per second at 0 degrees C. Speed of sound in air. So in air, so we know air, the particles are far apart now. Air, the particles are far apart, so the speed of sound will not be that fast. But in water still has the particles closer together. In concrete, the particles are very close together, so speed of sound will be high in concrete. It will also be high in glass, where the particles are closer together, so it will be a bit higher than in water. It will be higher in water than in air, because air is a gas. Okay, so the speed of sound in water is 1500 meter per second. So this is the speed of sound in water. So let me just use VH2O to simplify it. This is the speed of sound in water. Then the speed of sound in steel, like a solid material. Speed of sound in steel, V steel, is very high. It is it is 5,000 meter per second. So you can see why because still the particles are very, very closer together. They're very close, so the particles will make the sound to travel very, very fast. Okay, so take note of that. Jamb can ask you that part. Then move to reflection of sound. Now, when you're doing reflection of sound, you talk about echo. Echo is just what happens when sound waves are reflected back. And when you're doing echo, use this formula. Very, very important. V is equals to 2D over T. This formula will give you the answer to any echo question in Jamb. So the reason why it is 2D, because the sound wave, when you shout, hello, 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 because of the echo, the sound wave will travel like this, cover distance D. It also bounce back when it hits the medium. So it will bounce back. So it will cover two distances. Like it will go, then come back. I know speed is distance over time. So V will now be total distance covered is 2D divided by the time. So very, very important. So reflection of sound waves causes echo. Okay, causes echo. Now this echo can be used to find the depth of this ocean. Also used to use it to as in for oil exploration. Even that is what bats are using to see or find their food. So bats use what is called echolation. Echolation to locate their prey or to find their food and stuff like that. So we move to the next one, which is interference of sound. Interference. So interference. So I told you guys there's constructive interference and there's destructive. So when two sound waves of different frequencies, like someone is here talking or shouting at frequency F1, someone is here talking shouting at frequency F2, these two waves can interfere. And when they use a beat, so beat is just F1 minus F2, just subtract the frequencies. It cannot be negative, or it must be positive. So subtract the smaller one from the bigger one. That will give you beats. Beats of when you hear beats, it means subtract the frequency. Okay, so I hope you understand that part. So this is superimposition of two sounds. The sound from here and the sound from here will be superimposed. And once they become superimposed, it will produce a beat. The beat is given by F1 minus F2. So, any questions? I hope you are following. So, we move to the next part, which is pitch. This part, pitch. So, pitch. Pitch of a sound. You know how children scream now, like ah, how children used to scream. There's a way they scream that even adults cannot scream like that, but some girls can scream like that. That tiny loud pitch, that loud sound that they make when the child is screaming or when they cry, that's pitch. So the pitch of a sound is a measure of the depth of its tone. Okay, and this depends on the frequency. So the reason why babies can scream like that is because the sound has a high frequency. That's a high frequency. Okay, that is why they can scream like that because of the high frequency. So they might ask you, OBJ, take note, pitch of a sound depends on frequency. Pitch of a sound, the pitch depends on frequency. So take note, please take note. Jamb can ask you. I'm sure they have asked many times. Pitch of a sound depends on the frequency of sound. So you can also have what's called a deep low pitch. A deep low pitch, or like bass. You know, when somebody's talking with bass, like heavy voice. That voice is thick. You know, you say, this guy has a thick voice. The voice is thick, but the frequency is low. If frequency is low, the voice will be thick, like bass. Thick bass, like people that have strong voice. You understand? Then if the frequency is high, this one is for low frequency. If the frequency is high, if the frequency is high, to produce what is called a shrill. A shrill is all this loud sound. Not loud as in heavy sound, but it can affect your ear. They call it sound that birds make, really, like as in like dogs. When the dog is in pain, the dog will give out a shrill. It will give out a shrill. Okay, that shrill has a very high frequency. Now the human ear is capable of detecting sound wave, but it's not all the sound waves that we can hear. There's some sound waves that human beings cannot hear. These are sound waves that are more than 20,000 hertz. Let me say 20 kilohertz. Any sound wave that has this frequency, when the frequency of a sound wave is greater than 20,000 hertz, that sound is called ultrasonic. Ultrasonic sound. So human beings cannot hear ultrasonic sound, but some animals can, like dogs and cats and stuff like that. So human beings can only hear sound frequencies that range from 20 hertz to less than, at least maybe less than 20 kilohertz. But anything that's above 20 kilohertz, it becomes ultrasonic. So audible sound that you can hear from music, TV, audible sound, this is the frequency. But one that is ultrasonic that you cannot hear, though other animals can hear it. That is why dogs are very, very sensitive. Other animals can hear it. Those ones are frequency above 20 kilohertz. So I hope you get that part. The next one we move to is what is called intensity. So for intensity, we're talking about loudness. Intensity has another name. The name is loudness. How loud is a sound? That is the intensity of the sound. So the loudness of a sound or intensity of a sound at any point is a measure of the power transmitted by that sound or by the wave through a point. Okay, it depends on the amplitude. So loudness depends on amplitude, not on frequency. So take note, it depends on amplitude. The loudness of a sound depends on the amplitude. Amplitude like this, the highest height here, the number that is here, the highest height. Because at this point, this is where you have the loudest sound. So for you to have the loudest sound at this point, then this guy must be very, very high. So it depends on the amplitude, not on the frequency. Loudness does not depend on frequency, but pitch depends on frequency. Why pitch does not depend on amplitude. Okay, hope you get that part. Now we'll move to what is called vibrating strings. Vibrating strings. Now for vibrating strings, you need to take note of this thing, this formula. This is the base formula for vibrating strings. F is equals to 1 over 2 pi square root of T over M. This formula is very, very important. You need to memorize it. F is equals to 1 over 2 pi square root of T over M. So F is the frequency as usual. Pi is 20 over 7 as you know. T is the tension, which is how tight that string is. In a guitar, you have to tie the string tight. Okay, otherwise it's not produce a good sound. Then M is the mass per unit length of the string. The mass per unit length. So they'll give you the mass of the string divided by its length. That's what will be M. This M is not mass, so it is the mass divided by the length of the string. It means how thick. This one just means how thick is the wire. That's just the meaning. How thick is the wire? That's this guy. That's the M there. So several things can change based on this. For example, you can see how frequency relates to other things. Take for example, if the tension is high, frequency is at the top here. It is directly proportional to the tension. Frequency is directly proportional to tension, as you can see here. If tension is high, frequency will be high. What does it mean? If you have the guitar and you tie the the string very tight, as if it wants to cut. Very tight. You just once you pluck it or you just strike with your finger a little to produce a very like a high shrill. The frequency will be high, to sound high. You give it a high note. That's because frequency and this one are proportional. But if you tie it in a very loose manner, it's not too tight, then to give it a low frequency. The next one is frequency and the thickness. So frequency is inversely proportional. You can see. This one is under. This one is at the top. If you put over here, you will know. This one has gone under. This one is at the top. So frequency and the mass per unit length or the thickness are inversely proportional. That means if the frequency is high, this one will be low. If this one is low, frequency will be high. Okay, so let's assume this one is very high. That means it's very, very thick. The wire is very, very thick. Then it will give you a low frequency. If the wire is very thin, it will give you a high frequency. So they are inversely proportional. So just bear that in mind. So you don't have any challenge. So that is how frequency relates to the tension and the mass per unit length. So the tension is measured in Newton. This is a force measured in Newton. Okay, so at times in some books you will see L here. They can also put L here. So you can also see it like this. F is equals to 1 over. If the L, that's if the L is not constant. But you can also have it like 1 over 2L square root of T over M. So if the length is varying, they will show the length there. So this is the length here. The frequency is inversely proportional to length too. So you can see. If the length is very long, the frequency will be low. If the length is low, frequency will be high. That is why if you have a short bottle, if you have a bottle like this is a short bottle here, just an absorption, and a taller bottle or a thin bottle. If you blow breeze at the top like this one has a shorter length of air column inside it. Since this one is shorter, that means this bottom part is short. This one will give you high frequency. This one here, the frequency here will be high, very high. But in this tall bottle, the bottle is long. So this place, and this bottom part here is high. So this place will be low. Frequency will be low. This one will give you a low frequency. So just keep this in mind. These are things you need to take note of. So don't forget this formula. It's also called the pseudometer formula. F is equals to 1 over 2L square root of T over M. So I hope you get that. Then we'll move into what is called the overtones now. Overtones and harmonics. So you have harmonics, and overtones. So starting with the basic overtone. So for harmonics is just you hear the fundamental frequency. It's just the first loud sound that you can obtain in maybe a particular instrument. That first loud sound is called F naught. The symbol is F naught, fundamental frequency. And for a standing wave, it looks like this. You have one here, you have one here. This is like a wall. This is like another wall here. So for a stationary wave, this one goes like this. It hits the wall and comes back like this. So this place will be a node because there is no movement here. It could also be a node. The middle like this is an antinode because an antinode lies between two nodes. So you can find this distance. What will be the length of this air column inside here? You understand? What will be the length of this part? This is L. So you can find this L knowing that dn to n, distance from node to node, is lambda over 2. So that means L is equals to lambda over 2. Okay? So you can see that this is the point where you have what is called the fundamental frequency to occur when the string is like this. Then another time where it's going to occur is if you have double of this. So you have like this 1, then you now have another one again, 2. Like this. This is double of it. Because you want to sound it the second time, so you put double of it. This is the first time it's going to have a loud sound. The second time it's going to have another loud sound. So from here, this is a node, this is node, this is also node, this is also node. So you need to find this distance from here to here like this. So we already know that from node to node, this is node to node already. That is lambda over 2 plus this another node to node, lambda over 2. If you add this, you're going to get 2 lambda divided by 2, which will give you lambda. 2 cancel 2. So the length is equal to lambda. So at this point, you're going to have what is called 2FO. Okay, 2FO, or the second fundamental frequency. Then for the third time, let me just draw this one. I'm not calculate it because of time. So for the third, if you want to sound the third, give it the third highest sound, you're going to draw 3 of this thing. So you're going to do like this. 1, 2, that's the first one. 1, 2, the third one. 1, 2. This is next time to give it the next higher sound. So you have node, 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 and node. Then you can do the calculation and get your answer. So bear that in mind. So you can, in this standing wave, which looks like this, you can have what is called fundamental frequency, which is F naught. After F naught, you can have 2 F naught, then you have 3 F naught, 4 F naught, and so on like that. So this F naught is the fundamental frequency. This one here, this next one here, is called the second fundamental frequency, or you can call it overtone. This one is first, this is fundamental frequency here, that's this one. But this one here is called first overtone. That's on that way. First overtone. Okay, this one is third overtone. Sorry, second overtone. Second overtone and third overtone. So just take on the formula. Once it's 2 F naught, that is first. You bring the power down by 1. 2 minus 1 is 1. So this will be first overtone. 3 minus 1 is 1. 3 F naught will be second overtone. 4 minus 1 is 1. 4 F naught will be third overtone. Okay, so I hope you understand this. Then from this place, you can put it in the formula. Depending on what they give to you, you can put it in the formula. For example, now, since you have seen that for the fundamental notes, that is when it is like this in a stationary string, this is L equals lambda over 2. So you know that L is lambda over 2. From here, lambda is equals to 2L. I know that V is equals to F now. So V will now be, this is fundamental frequency F naught. F naught. Now instead of writing lambda, don't write lambda again. Just put this guy here. 2L. So V will just be 2F naught L. Okay, so I hope you understand. V is equal to F lambda is the general wave equation. So I hope you get that part. Okay, so this will bring us to the end of this stream. I hope you understand. I'm going to put the second section very soon, the continuation parts of this video. Thank you for watching. I really appreciate you. Thank you for joining me in this live. I'm going to post more to the conclusion part of this. We're going to talk about open pipes and closed pipes. That's just the remaining parts. So thank you for watching EduMaths. Please subscribe. If you have not subscribed, please subscribe. Subscribe. I appreciate you. Subscribe. Thank you for watching. Remain blessed. I'll see you guys later. Okay.